Imagine looking up, well, not literally looking up, but thinking about our solar system and finding objects that just don't fit. They look like asteroids, rock solid, but they act like comets.
But without the fireworks, right? No big dusty tail.
Exactly. Just this weird behavior. Scientists are starting to call them dark comets.
The category, yeah. And they're fascinating because they might help answer some really big questions.
Huge questions. Like, where did Earth's water come from? That's a classic.
And maybe more urgently, do these things pose some kind of threat we didn't even know about?
Right. So for this deep dive, we're going to sift through what scientists are finding out, including this incredibly lucky encounter with a Japanese spacecraft.
Yeah, we want to pull out the key things you need to know about these cosmic mysteries.
Okay, so if they're dark and kind of subtle, how did we even notice them? Where did this start?
Well, the first real inkling was back in 2016. Astronomers saw this object, looked like a standard asteroid, nothing special visually, but it wasn't moving quite right. It showed what they call non-gravitational acceleration.
Which normally means?
Normally means it's a comet. Ice heats up, releases gas and dust, tiny jets pushing it around. Standard comet stuff.
But this one didn't have any of that.
None. No visible tail, no fuzzy coma around it, nothing. Yet something was definitely nudging it, just tiny pushes, fractions of a meter per second.
But noticeable over time.
Exactly. You track it long enough with telescopes, you see it drift off the path gravity alone would dictate.
And then didn't Oumuamua do something similar just a year later?
It did. 2017, Oumuamua zooms through from interstellar space, that weird cigar shape. And yes, it also had that strange, unexplained acceleration. Different origin, obviously, but same puzzle.
Made people think maybe this isn't just an interstellar thing.
Precisely. So the hunt was on in our own system. Cut to 2023, and astronomer Daryl Seligman's team announced they'd found 6 more.
6 objects orbiting our sun.
Yeah, orbiting the sun, looking like asteroids, no tails, but doing that little speed burst thing.
Were they big?
Pretty small, actually, between maybe 4 and 32 meters across. And the push was minuscule, like 1 nanometer per second squared acceleration.
Nanometer? That's incredibly tiny.
It is, but it adds up. Enough to shift them hundreds of kilometers off course over a few years. They also tagged a bigger one around then, 2003 RM, a near-Earth asteroid, about 300 meters. It was doing it too.
So the list started growing. What's the count now?
Last update, December 2024, they were up to 14 known dark comets in our system.
14, okay. Still not a huge number, but definitely a pattern emerging. But what's actually causing it?
Well, that's the million-dollar question. Even Seligman basically said, we still have no clue what's actually causing it.
Right, that's the core mystery.
It really shakes things up. We used to have this neat picture, you know? Rocky asteroids in the innerish parts, icy comets way out past Neptune swooping in with tails.
Yeah, the clean categories.
But as astronomer Matilster put it, that picture has completely gone. It's looking more like a continuum, a messy spectrum between rock and ice.
Okay, but wait, aren't there already things called active asteroids? How are these dark comets different?
Good question. Active asteroids, which we've known about since '96, they do visibly eject stuff. You can see dust or gas coming off them, usually because some ice got exposed.
So you can see the cause, more or less.
Right. The crucial thing with dark comets is no visible signs. They accelerate, but you can't see anything being thrown off.
And it's definitely not just the Yarkovsky effect, that heat radiation thing.
Apparently not. Teddy Carreta, another astronomer working on this, specifically said they're drifting faster than the Yarkovsky effect can explain.
So some other force is at play, something we haven't accounted for.
Seems like it, which makes getting a close look absolutely vital.
And this is where that spacecraft story comes in. Hayabusa 2.
Exactly. So Hayabusa 2, the Japanese mission, did amazing work at asteroid Ryugu. Brought back those samples in 2020, full of clues about water and maybe life's building blocks.
Yeah, incredible mission.
But after dropping off the samples, the spacecraft was still healthy, still had fuel. So JAXA, the space agency, thought, hey, let's send it somewhere else.
An extended mission. Where do they pick?
They picked an asteroid called 1998 KY26. It had some interesting, peculiar properties they wanted to check out.
Okay, and let me guess.
You got it. Turns out, completely by coincidence, 1998 KY26 was later identified as one of Seligman's dark comets.
No way. They picked it before they knew it was a dark comet.
Totally unknowingly. Yuichi Tsuda, the mission's project manager, basically said, yeah, we had no idea about dark comets when we planned this. It's really exciting. Pure scientific serendipity.
That is amazing luck. So what's special about this target, 1998 KY26, besides being a dark comet?
Well, for one, it spins incredibly fast, like once every 10 minutes. And it's tiny, only about 30 meters, maybe 100 feet across. If Hayabusa 2 gets there in 2031 as planned, it'll be the smallest object ever visited by a spacecraft.
So 2031 rendezvous. What's the plan when it arrives?
First, they'll hang back a few kilometers. Just watch, take pictures, try to see if there's any faint outgassing, any ice melting that ground telescopes might miss.
To see if it's just super faint cometary activity.
Exactly. Seligman thinks if it is comet-like outgassing causing the push, Hayabusa 2 should definitely spot it up close.
And if they don't see anything?
Well, later they might try to get closer, maybe even descend. It still has that impactor on board, the bullet thing it used at Ryugu.
To make a crater.
Yeah. Sita mentioned that by watching the stuff thrown out by the impact, they might figure out the internal structure. It's solid, rubble, icy inside.
That could be huge. Direct physical evidence.
Absolutely. And while we wait for 2031, other work continues. Teddy Creed is using the Lowell Discovery Telescope to keep observing these things, measure their weird accelerations, try to get composition data when they brighten up.
Is JWST, the Webb telescope, looking at them? Seems perfect for faint things.
They'd love to use it, I'm sure, but getting time on Webb is incredibly competitive, especially for, brand new mysteries like this. It's tough.
Right. Always a bottleneck. Okay, so we have observations ongoing, a spacecraft heading towards one. What are the leading theories right now for why they behave this way?
One promising idea comes from Astor Taylor's group. They suggest maybe these start as normal asteroids out in the main belt, but they have ice trapped inside them.
Hidden ice.
Then something, maybe Jupiter's gravity, knocks them closer to the sun, and at some point they split apart.
Just break up.
Could be from spinning too fast, or maybe they get hit by something smaller. The point is, this exposes that internal ice to sunlight for the first time.
And boom, instant dark comet. The ice starts vaporizing, but maybe not enough to make a visible tail, just enough to push it.
That's the idea. And it fits with another clue.
Right.
These things spin really, really fast. Some clock in at once every 6 minutes. Way faster than similar-sized asteroids.
So the fast spin might be linked to the breakup event and maybe helps the subtle outgassing?
It's all connected in the theory. Yeah, the spin could be key.
And didn't you mention there might be different types of dark comets?
Right. That was a hint from the December 24 data. It's not just one thing. There might be two flavors.
Okay, what are they?
First, outer dark comets. These seem larger, maybe 100 meters up to a kilometer. They orbit out near Jupiter. Kurita suggested these might actually be old, dying comets.
Like they've run out of most of their ice, just have a tiny bit left, running out of gas, as he put it?
Exactly. We're seeing them in their twilight years. Then there are the inner dark comets.
The lower ones.
Yeah, smaller, maybe 10, 20 meters. And their orbits are more circular, more like Earth's. These could be the broken apart asteroids with the exposed ice, like Taylor's theory suggests.
Huh. So two different paths leading to this same weird hidden acceleration. That really does blur the lines.
It really does. Asteroid, comet. Maybe the labels aren't as useful as we thought for some objects.
Okay, let's bring this home. The so what factor. Why does this matter to us here on Earth? Let's start with the water question again.
Right. Big theory is water came to Earth via impacts from asteroids or comets billions of years ago. If it turns out a lot of asteroids near Earth are actually these dark comets with hidden ice.
We just didn't realize they were carrying water.
Exactly. Seligman's point was, if there are lots of hydrated objects nearby we didn't know about, they could have been a much bigger source of Earth's water than we calculated.
That would definitely rewrite some early Earth history.
Yeah.
What about the danger aspect? The impact threat?
That's the other side. Imagine tracking an asteroid. Its orbit looks safe, predictable, but if it's a dark comet...
It could suddenly get that little nudge, change course slightly?
Yeah, and over time, that slight change could be the difference between a near miss and, well, something else. Astor Taylor said, you can have an Earth impactor that you didn't expect.
That's sobering. And we know some of these are near-Earth objects.
Several are, yeah, including that bigger one, 2003 RM. It's in our neighborhood.
So, correctly identifying these things, understanding that hidden push, becomes crucial for planetary defense.
Absolutely critical. If you can't model their orbits accurately because you don't know about this extra force, you can't reliably predict if they're a threat. Taylor put it bluntly. If we can't detect these objects correctly, we will not be able to know if they're going to hit us.
Okay, need to be clear though. Right now they seem pretty rare, and the course changes are small.
For now, yes, they don't seem to be darting around wildly, but the fact that this mechanism exists and we don't fully understand it, that's the key takeaway. The mystery demands attention.
It really is fascinating how these dark comets are forcing us to redraw our map of the solar system, isn't it?
Yeah.
And missions like Hayabusa 2, plus the ongoing observations, they feel like they're right on the cusp of potentially solving this.
It feels that way, yeah.
Right.
We're definitely peeling back layers on a complexity we just didn't appreciate even 5-10 years ago. It's exciting, scientifically.
Yeah, definitely exciting. And it just leaves you with this thought, doesn't it? If objects we thought were just inert rocks can have these hidden engines changing their paths, what else is out there hiding in plain sight, behaving in ways we haven't even conceived of yet?
What other physics are we missing in the motions of the heavens? It's a big question.